Good morning. I'm very glad to be here with many friends I didn't see before a long time. So what I would like to talk about is an example of mathematical model in the age of data. What does this mean? I think that data, more than anything else before, posed a big challenge, and this challenge is multidisciplinarity, and inside mathematics, interdisciplinarity, as even both Professor Lillo and Bottazzi show in their talk somehow. So what I would like to do here is to elucidate this phenomena with an example. I hope at the end of my talk, I will be able to conceive this message. So, okay. So at the beginning, I will tell you about motivation, so how we started. Then the challenge that data posed in this in production theory, how we try to answer to this challenge, and then in okay, so what happened here? Here. And then the second part will be about interdisciplinarity, because this model is discrete model, but we needed to embed it in a continuous setting. Okay. While the third part will be the results obtained thanks to the continuous setting and some statistics that we apply to those results. Okay. So the let's say the real problem we started from was production theory. So a firm productivity is just nothing else than the ability of a firm to produce output starting from some input. So you can think about capital and labor and how firm use capital and labor to produce services or values or whatever else, okay? Classically, this problem is handled by a parametric approach. So the existence of production function is assumed, which tell how the firms inside an industry behave. So which are the issues of this approach? The first is that the choice of a production function is based on a priori assumptions. Okay, so which are both macro and microeconomic level. In particular, we also assume that firms tend to maximize profit and minimize costs. But the most interesting part, the one I would like you to focus in, is the homogeneity towards heterogeneity. Essentially, this approach assumes that firms inside an industry are homogeneous. To give you an example, it assumes that 3 students creating an app in a garage use the same function of Google. Okay. What happened? Data showed highlight a strong and persistent heterogeneity in this production process. So data posed the challenge. Is it possible to create an alternative model which is based on data without taking functional forms assumption and which takes into account the existence of this persistent heterogeneity? We tried to answer to this problem in a joint work, in a couple of joint papers with Dossi, Grazzi, Marengo, and then Le. In those papers, with the redefined productivity starting from the data, we introduce a method to assess heterogeneity in an industry. And finally, we use this to estimate important aggregate indices. What I would like, again, you to focus in the second point, heterogeneity, okay? Now, in the rest of the talk, I will elucidate this. So both the method to assess heterogeneity and subsequent development we did with Terni, Franciosi, and Lee. Okay, we started with a discrete model. This was introduced by Hildebrand. So essentially, Hildebrand what just said, okay, each firm is a point in the space, on the positive octant of space. So you can think, if you think in terms of capital, labor, and output, we are just in a three-dimensional space. This is the best way to imagine this. So an industry is just a bunch of points in the positive octant. N will be the number of firms, and those are our points, okay? So then we define the following Hildebrand. The production set is the vector joining the origin with each firm, representing by a point. This is firm, but can be whatever, any data, okay, which is represented by a point, okay? So any data. And then we define the total production set has the zonotop, is the Minkowski sum, okay, of all these segments. So it's the weighted sum of those points with weight going from 0 to 1. The result is this geometrical figure called zonotop, which is the main object of study on discrete mathematics that nowadays called combinatorics. So our industry can be represented by this zonotop, okay? So in this case, we have, I would like just very easily, you have just the sum. So you have 4 vectors in this case, and the zonotop is just all possible sum that we have. So the zonotop represent our industry, okay? So what we have here, how we interpreted this in terms of heterogeneity. The main idea is more heterogeneous are the firm, so more sparse are the points, fatter will be the zonotop inside the parallelotop containing it. So this is the way we defined this index of heterogeneity simply as the quotient between the volume occupied by the zonotop and the volume of the parallelotop which contain it. So just going back here, so the volume of this zonotop quotiented by the volume of the parallelotop. We call it Gini volume. Why? Because this is nothing else than one possible multidimensional generalization of the well-known Gini index. Okay. Now, the problem is when we have a lot of data, especially in high dimension, how we can compute this volume. The answer is to use random sample, but then we need to prove that this index we defined is somehow robust, meaning that we can use subsample to compute this index instead of all the entire sample of the firms inside the industry. And then we had to use continuity. So we started with a real problem, we modeled it discretely, and now we embed it in a continuous setting to use continuous tool to get what we want. Okay, just checking for time. Okay, the continuous setting is the measure, is inside measure theory. Okay, so the thing is that, sorry, what did I do? Okay, I went ahead. Okay, so the above approach, of course, is non-parametric. So this is h point in the zonotop can be seen as the integral of a suitable function with respect to discrete measure mu, where dy, delta y, is the Dirac measure which assigns mass 1 to point y. Okay. So this is the discrete. In this framework, the Gini volume can be regarded of the measure mu. Dispersion index of the measure mu. So we have now our continuous setting. We can consider in the set of Borelian measures, which are finite, non-negative, and with finite prime momentum. We can define the mass of this measure, m mu, and we define the zonoid associated to the measure mu as essentially all the possible masses with the function, with a weighted function phi valued in 0, 1. Okay. What are zonoid? Zonoid are nothing else than the continuous companion of zonotopes. Essentially, zonotopes are the rational numbers, zonoid are the real numbers. And indeed, as happened for rational real number, zonotopes are dense subset in the set of zonoids. So we are really in a good continuous setting. Okay, and the empirical zonoid associated to an empirical distribution, the one we have seen before, so discrete distribution, is indeed a zonotope. So now that we have our continuous setting, we can study robustness. We can generalize the Gini index and study robustness. The obvious generalization, I will jump this. The obvious generalization, it's simply to consider the Gini volume, the Gini index associated to the zonoid Z mu, and it will simply be the volume of this zonoid quotiented by the volume of P mu, which is nothing else than all the element between 0 and the mass m of mu. Okay, so this is, sorry, this is a mistake. Okay, so this is nothing else than the continuous generalization of our zonotope, but you can keep thinking in terms of discrete, which is always easier somehow. At this point, what is left to do is just study limits and robustness. Okay, so if we have a sequence of Borel probability which are positive, finite, and everything as before, if converging to mu in P1 plus, if the sequence of their mass converges to the mass of mu, then the sequence of the Gini indices of the zonoids converge to the Gini index of the zonoid Z mu. Okay, and this allowed us to use an equivalent of law of large numbers, meaning that if we have a sequence of random variable with distribution mu, and we have a family of empirical distribution, then each defined starting from those random variable, if those empirical each of those empirical distribution is contained in P1 plus, and the Gini volume, as we expected, of the Z of this empirical distribution converge to the Gini index of Z mu, of the distribution mu of our random variable. And it does it with probability 1. So essentially what this result told us, this result simply told us that we can use subsamples. Okay, now which kind of subsamples, how big and so on, this needs still to be studied. But what we do, we did some, I will show you now some computation. Okay, we did some computation. We started from a sample of 100 different Italian industries, each one between almost 400, around 700 firms. And we studied subsamples of size 10, 20, 30, and 40%. And we check how different the study of the how much the subsample differ from the real value G. Those are the results. The majority of industry, like the 80% of industries behaved like this, telling us that 40% with these few firms is already good approximation. Of course, bigger is the industry, lower will be the subsample needed. Okay, for these industries are very small, 400 firms, so the sample is 40%. But what I would like you to point the attention on is here. 25% of our firms believed in a different way. And this opened totally new possibilities. Why? They already with 10%, we get a very good approximation. And the more we sampled, the more the distribution became with several peak. Okay, what this means, what those peaks means? Our idea is that they tell us that the industries we are considering are clustered, meaning that instead of being well distributed in the space, they cluster in few similar techniques, which give rise to this behavior when we sample them. So the conclusion are, maybe this is not only a way to solve the problem of simplified computation, but this Gini index can also tell us a new way to investigate techniques inside the industry. I answered to important questions like that, there are techniques which are dominant in a given industry. Are the dominant techniques the most efficient ones? And is the efficient of those dominant techniques predictive of future growth of the industry? So those questions are important in industrial economics, and this could provide a new way to investigate them from a totally different point of view. Okay, so that's all. What I hope you got from this is that data really need all of us.